All right, let's talk about statistics. And I know, the word itself can make your eyes glaze over. You're thinking charts, graphs, maybe a boring math class you once took. But what if I told you statistics is actually a superpower? Seriously, it's the science of finding the truth in a world that is just full of random noise. It's how we go from a wild guess to a real guarantee. Okay, let's put you in the hot seat. Imagine you're running things at Netflix. Your design team has this great new idea. Maybe they've changed a button color or tweaked the algorithm that recommends shows. They swear it's going to get people to watch more. But how do you know? How can you be absolutely sure it's better before you push that change out to hundreds of millions of subscribers? Well, you can't just ask people, right? People say all sorts of things. You have to test it in the real world. So you do something called an A/B test. Most people, let's say 99%, keep seeing the original interface A. But a tiny, random 1% gets the new interface B. Then you just sit back and measure who watches more. Simple enough, but billion-dollar decisions are riding on the answer. And that answer is way trickier than it looks. To really get why this is so hard, we have to talk about a fundamental problem. Not with Netflix, not with buttons, but with reality itself. Think about pure math. It's clean. It's predictable. If x is 2, then 2x is always 4. 100% certainty. No questions asked. But the real world? Oh, the real world is messy. I mean, just measure one person's viewing habits, then measure another's. You're going to get different results. People are different. Our moods are different. Everything varies. And that one word right there is everything. Variability. It is the single reason the entire field of statistics has to exist. I mean, if everyone was exactly the same, if we all acted identically, you'd only have to test that new Netflix button on one person, and you'd have your answer. But we don't, and so we need a tool to cut through all that mess. So how does statistics deal with this messy, variable world? It uses a really clever strategy. It grabs a small piece of the truth to figure out the whole story. So let's get two key terms down. First, you have the population. That's the entire group you want to know about. For Netflix, that's every single subscriber on the planet. It's huge, right? Way too big to measure, so we use a sample. The sample is just a small, manageable chunk of that population that we can actually study, like that 1% test group. And this leads us to the basic game plan for all of statistics. It's kind of like a loop. First, you ask a big question about the population. Then you go out and collect some data from your little sample, you describe what you found in that sample, and then, and this is the magic trick, you make an educated guess, or what statisticians call an inference, about the entire population. You use the evidence from the few to make a conclusion about the many. Okay, so we've got our data from the sample. We're ready to go, right? Well, not so fast. Before we do any number crunching, we have to figure out what kind of data we're even looking at. Because, believe me, not all data is created equal. At the highest level, data basically comes in two flavors. You've got qualitative data, which is just labels or categories. Think eye color, blue, brown, green. You can't do math on that, right? What's the average of blue and green? It's meaningless. Then you have quantitative data. These are actual numbers you can measure. Think height or weight or temperature. Here, doing math, like finding an average, actually tells you something useful. But this is where it can get kind of tricky, because numbers can be deceiving. Take a zip code. It's a number, but you can't do math on it. It's just a label for a place, so it's qualitative. You can't average the zip code for Beverly Hills in New York City and get Chicago. Or look at shoe size. That's a number, but it's not continuous. It only comes in fixed steps, like 8, 8.5, 9. And then there's something like temperature, which is truly continuous. Between 70 and 71 degrees, there's an infinite number of other temperatures. Knowing what you're dealing with is absolutely step one. And we can go even deeper, because even when you're dealing with numbers, there are different levels of measurement, and each level has its own strict set of rules about what kind of math is actually allowed. So, real quick, there are 4 levels. You've got nominal, which is just names, like we talked about. Then ordinal, where the order matters, like a movie rating. 4 stars is definitely better than 3. Then you have interval, where the spaces between numbers are equal, like degrees on a thermometer. And at the top, the most powerful level is ratio. This is special because it has a true meaningful 0, which means you can do any kind of math you want. And that distinction brings us to this amazing little puzzle that shows why these rules matter so much. So here's the question. Is 80 degrees Fahrenheit actually twice as hot as 40 degrees Fahrenheit? I mean, on the surface, it seems obvious, right? 80 is just 2 times 40. So, yeah. But is it really? Well, think about it. If that twice as hot relationship is a real physical fact about the world, then it should be true no matter what units we use, right? So let's just check our work by converting to Celsius. 40 degrees Fahrenheit is about 4.4 Celsius, and 80 Fahrenheit is about 26.7 Celsius. Okay, now let's see what happens to our twice as hot idea. And boom, there it is. In Fahrenheit, the ratio was 2. But when we look at the exact same temperatures in Celsius, the ratio is over 6. 2 is not equal to 6. The relationship completely vanished. That whole twice as hot thing, it was just a mathematical illusion based on the scale we were using. So why did that happen? It's because temperature in Fahrenheit or Celsius is an interval variable, not a ratio variable. And the reason is, it doesn't have a true zero. Think about it. 0 degrees Fahrenheit doesn't mean there is zero heat. It's just a random cold point on a man-made scale. And if your zero doesn't mean the complete absence of the thing, you just can't make claims like twice as much or half as much. The math doesn't work. Okay, let's bring this all back home. We've gone through variability, samples versus populations, different data types, and these tricky levels of measurement. So how does all of this get us from a shaky guess to a confident statistical guarantee? Let's look at that Netflix problem again, but this time with our new toolkit. The population is all subscribers. Our sample is that 1% test group. The thing we're measuring, time spent watching, is quantitative. And, here's the key, it's a ratio variable, because 0 minutes of watch time really means no watching at all. It has a true zero. So, if we see that our sample group watched 5% more, we can now use the proper tools of statistics to calculate the exact probability that this 5% bump is a real effect, a true signal, and not just some random, meaningless noise caused by all that variability we started with. And really, that's the whole point. This isn't just about giant companies like Netflix. I mean, think about your own life. Choosing a new workout plan, trying a different diet, figuring out the fastest way to get to work. Our lives are just packed with variability and noise. So the real question to leave you with is this. What decisions in your life could you make with way more confidence if you just had the tools to separate the real signal from all that random noise?